when we deal with electricity, we're going to have to deal with different types of materials. For example, some of them are going to be conductors, some are going to be insulators, some are going to be semiconductors, and even sometimes we talk of what we call superconductors. Now, what we define as a conductor is a material where the electrons, remember all materials are made up of atoms, but in the case of the conductors, electrons from the outermost shell of the atoms that make up that material are free to move within the conductor. Essentially, what I'm saying here, each of the atoms making up that material are going to let loose of their outermost electron. And then what that means, that outermost electron is going to wander around freely within the conductor. Now, this stopped from playing. Let me go back. Okay, good. As you notice here, if we approach a positive charge to a conductor, then the negative charges are going to be attracted to that positive charge. If we approach a negative charge instead, the negative charges are going to be repelled by that charge. Now you notice we didn't touch it in any of these cases. Now what I want you to pay attention to is the fact that the electrons, when we don't have a charge nearby, are spread out evenly throughout the conductor, because each of the electron is being repelled by the other electrons in the conductor. Now, so the position of equilibrium is when they are spread out evenly throughout the conductor. But then we'll talk more about that later on. Now, when we approach a positive or negative charge from the outside, what's going to happen? Since the electrons are free to wander around, they are going to be repelled if the charge we approach is negative, and attracted if the charge that we approach is positive. And that's what you see here, I hope. Now, what I want you to notice, the electrons are moving throughout the material. And you notice that here actually we don't see the protons moving. In real life, the protons are going to move also, but they are going to move just a little bit while remaining in place. They are just going to wiggle a little bit. But the only appreciable motion is going to be the motion of the electrons. One reason that you might want to think of why the protons do not move that much, it's because they are about 2,000 times as massive as the electrons. A proton is about 1,800 times the mass of an electron. So it's much more massive. When it is subject to the same kind of force, it's not going to accelerate that much, and that's why we don't see it moving much. In the case of the insulators instead, you notice here the electrons actually move, but they move in place within the atom. So when we approach the negative charge, you see the electrons move to the opposite charge of the atom from that negative charge. And then in the next layer, the electrons are going to be repelled again. So effectively, we are going to have an abundance of negative charges at the bottom and positive charges at the top. So effectively, we are going to see the same kind of effect. However, the electrons themselves are stuck to their atoms. They are not going to move far away at all. One last thing about this. Most matter is between perfect conductors and insulators, and actually the conductivity of materials is going to depend on their temperature, and it depends in other cases on other factors like light and so on, light, heat, and so on. Now, there are superconductors, for example. They are even better than what we call perfect conductors. Currently, superconductors exist only at very low temperatures, temperatures below 90 degrees Kelvin, which is the liquid temperature of liquid nitrogen. But actually, most of the ones used commercially right now, they need even lower temperatures than that to operate as superconductors. Now, whenever we talk of static electricity, people will think of this experience here of having a balloon being rubbed on the hair or on the sweater or something, and then having it stick to a wall. What we are going to try to do is try to explain this. Notice here in the animation that we have, whenever the person rubs the neutral balloon, the balloon becomes negative and the hair becomes positive. And look here what happens to the wall. The negative charges in the wall are repelled, the positive charges stay in place, and then the negative charges of the balloon are held in place because of their attraction to the positive charges within the wall. There is a neat simulation that allows you to do the same kind of thing out of what's called this website here, FET website, fet.colorado.edu. I'm going to try to run it right now to show you a little bit. Actually, okay, see it here. So you come with the balloon and you rub it, and the more you rub it, the more charges it's going to accumulate. And then as we approach it to the wall, you see the negative charges being repelled, and there we go. Notice here that the charges also stay in place here because this is an insulator, meaning that the charges are not going to be able to travel easily around that insulator. Wherever you put a charge, that's where it's going to be stuck. Let's just play a little bit here. Let's have two balloons. So I have another balloon that's uncharged, and then I'm going to bring it here, and I'm going to collect some more charge, and you notice here, okay, see it repelled by the other one and attracted by the sweater in this case. Notice here that initially the sweater had positive and negative charges, and now we stripped it of quite a number of negative charges. And what we are seeing here is just the net charge that's left on the sweater. Okay, now we reset it again. So it looks like we don't have any charge. We rub it, and the more charge we accumulate here, the more charges are going to develop on the sweater. And if we approach it to the wall, it's attracted to the wall. And now here, same kind of thing. Okay. One point that I try to get across in doing the balloon and using the balloon simulation is we are going to always have charge conservation. The total number of charges is going to remain the same. Let's take an example here. What we have here, this is actually part of a simulation. You can run it as a simulation, but it's not necessary in this case. If we have two spheres, one with a plus charge of 7q plus 7q, and the other one with minus 3q. And then we put them next to each other. We make them touch each other. When we make them touch each other, these are made out of two conducting spheres. So what's going to happen when we put them in contact? Charges are going to distribute themselves uniformly throughout both spheres. Now, since both spheres are equal in size, they are going to distribute themselves uniformly, meaning that each of the sphere is going to have the same charge as the other one. Now, if we started with plus 7q and minus 3q, the net charge is going to be plus 4q, meaning both spheres together are going to have a charge of 4q, meaning that each one of them is going to have plus 2q. So once we separate them, each one of them will have a plus 2q charge. When we did rub the balloon, you notice we had on the balloon, we left negative charges, and on the sweater positive charges. Is that going to happen all the time like that? That's a good question. Are you sure we are going to have negative charges on the balloon, not positive? Or in other words, what determines the charge acquired by a certain material? Now, in these animations here, we have wool and PVC and wool and nylon. See, when we rub PVC with wool, we get the PVC to become negative and the wool positive. But the opposite happens when we rub the wool with nylon. The nylon becomes positive and the wool becomes negative. So the wool can become both negative and positive depending on what you rub it against. What's the reason for that? Now, whenever materials come in contact with one another, with a different material, whenever you put two different materials against each other, what's going to happen is, okay, this is my two materials against each other. The electrons in each of the materials are experiencing forces that are holding them to the material due to the atoms of that particular material. So an electron from here is subject to the forces from atoms from here. And the electrons from here are subject to forces from atoms from within there. Now, however, when the materials are close enough to each other, that especially can happen when you are trying to rub materials against each other. Now, when they are a close proximity of each other, it can happen that electrons from here can feel a stronger force from the atoms from the other side, and vice versa. That's going to happen all the time. If the two materials are identical, I'm going to have the same amount of number of electrons that are going to jump from one end to another, then from the other one to the other one. We say it some other way. Under normal condition, if I put two identical materials against each other, I'm going to have electrons moving from one to another, and the same number of electrons move the opposite way. That's going to happen all the time. However, when the materials are different, the material to the right might exert a stronger pull than the material to the left. So because of that, we might have a stronger migration from one end than from the other end. So because of that, when we pull the materials apart, each of the materials is going to gain a net charge. Now, that process is what we call triboelectricity. Now, triboelectricity it tells us that the polarity and strength of the charges in each material is going to depend on the material, like I just mentioned, which is what atoms is it made up of. It's going to depend also on the surface roughness, temperature, other physical parameters, the environment. Are we rubbing things in a humid day or not, in a hot day or not, and so on. Now, I'm not sure how well you see that, but there is a list that you can find everywhere, and there are many lists actually. But this one here I pulled up from Wikipedia after checking several others. What happens here, you have different materials. Like when I look here, human skin, leather, rabbit fur, glass, quartz, mica, human hair, nylon, wool, lead, cat's fur, silk, aluminum, paper, cotton, and so on. And we go down, then we have silicon, Teflon, silicon rubber, ebonite. Now, the more you go this side, the more positive this material will get if it's going to interact with another material. The more you go this way, the more negative the material is going to get. For example, we took the example of wool last time. Wool is here. So if wool interacts with one material from this side, wool is going to be negative and the material is going to be positive. Like we had the example there with leather, I believe, or I don't remember what it was. Let's see. Nylon. Okay, nylon, just next to it. Now, the other one, look at Teflon. It's all the way on the other side. So then in that case, wool becomes positive and the Teflon negative.